Have you ever wondered about that invisible force that kind of governs, well, everything? It's the reason you feel like you're getting pushed around in a car, and it's also why a satellite can just drift through space for years and years without ever stopping. Today, we're going to dive into one of the most fundamental rules of the entire universe, Newton's first law of motion, also known as the law of inertia.
So, to get started, let's think about something we've all felt. You're in a car, everything's going fine, and then, boom, the driver hits the brakes. What happens to your body? You fly forward, right? It feels like something is pushing you from behind. But what if I told you that nothing is pushing you at all? That strange feeling? That's the key to everything we're talking about today.
You know, before Isaac Newton came along and wrote down his famous laws, another genius, Galileo Galilei, was already wrestling with this exact puzzle. And he used a really simple thought experiment, just a marble and a few ramps, to completely flip how we think about motion. So to really get Newton, we first have to understand Galileo's marble.
Galileo's thought experiment was just brilliant. Okay, so first, imagine a marble rolling down a slope. It speeds up because of gravity. Simple enough, right? Then, when it rolls up the opposite slope, it slows down and it tries to get back to the same height it started from. But here's where it gets really clever. Galileo imagined making that second slope flatter, and then even flatter. The marble has to travel further and further to try and get back up to its starting height. So he asked, what happens if the surface is perfectly flat and totally frictionless? Well, the marble can never reach its original height, so it would just keep on rolling. Forever.
And this led Galileo to a totally revolutionary idea. You only need a force, like gravity on that slope, to change an object's motion, to speed it up or to slow it down. But to just keep it moving at a steady speed, you don't need any force at all. The natural state of an object is just to keep doing whatever it's already doing.
And this is where Sir Isaac Newton comes into the story. He took Galileo's amazing insight and he made it official. He formalized it as the very first of his 3 legendary laws of motion, giving us the rule that is the bedrock for so much of modern physics.
Let's just go through that slowly, because every single word here counts. An object remains in a state of rest or of uniform motion unless compelled to change that state by an applied force. All this really means is that stuff likes to keep doing what it's doing. If a book is sitting on your desk, it's going to stay there forever unless you push it. If a hockey puck is sliding across some perfect, frictionless ice, it's going to slide forever until it hits a wall. That applied force is just a fancy way of saying an outside push or a pull.
Now, this tendency for an object to resist changes in its motion, it has a name. It's called inertia. And it's important to remember, inertia isn't a force. It's not a push or a pull. It's just a property of matter itself. You can almost think of it as the built-in laziness of an object, its desire to just keep its current status, whether that's sitting perfectly still or moving at a nice constant speed. So how do you measure inertia? Well, it's actually pretty simple. We measure it with mass. The more mass something has, the more inertia it has. And that means the harder it is to change what it's doing. Think about it like this. Kicking a football is pretty easy. It doesn't have much mass, so it has low inertia. It doesn't resist being kicked very much. But now, try kicking a big, heavy stone with that same amount of force. Ouch. The stone has way more mass, which means it has way more inertia. It really resists changing its state of rest, and you're probably just going to end up with a sore toe. Okay, let's bring all this back to you, because this isn't some abstract law that only matters to scientists. You feel inertia every single day, especially when you're in a car or a bus. See, your body has mass, and that means your body has inertia. Let's break these down. When you're standing on a bus and it suddenly takes off, your feet go forward with the bus, but the rest of your body, because of its inertia, tries to stay put. The result? You feel like you're thrown backward. And when a car slams on its brakes, the car stops, but your body's inertia wants to keep moving forward at that same speed. That's that lurch we talked about at the beginning. Same thing when a car turns sharply. The car changes direction, but your body wants to keep going in a straight line. That's why you feel pressed up against the door. In every case, it's not a force pushing you, it's your own body resisting the change.
And understanding this isn't just about passing a test. It's absolutely critical for engineering and, maybe most importantly, for keeping us all safe. Because if your body wants to keep moving, we have to figure out a way to manage that tendency, especially when things go wrong.
So this brings us to the really critical, life-saving question. We know from Newton's law that an object in motion stays in motion unless an external force acts on it. Well, during a sudden stop, your body is that object in motion. Now, the dashboard could be that external force that stops you, but that would be, a disaster. So how do we stop you safely?
The answer has actually been hiding inside Newton's law this whole time. To change your body's motion, to slow you down from 60 miles an hour to 0, right along with the car, we have to apply a controlled external force here. And that controlled external force is the seatbelt. It's as simple as that. When a car brakes hard, the seatbelt locks up and puts a force on your body. It's designed specifically to overcome your body's inertia and slow you down at the exact same rate as the car, stopping you from flying forward. It is a direct, life-saving application of Newton's first law.
So you see, inertia isn't just a dusty old quote in a textbook. It's the reason you have to shake a ketchup bottle to get it started. It's how a magician can whip a tablecloth out from under a pile of dishes. And it's why the seatbelt is one of the most important inventions in history. Now that you see it, the question is, where else do you see this law at work, all around you? Thanks for listening.